Hello, everybody. This is Miss Lemens coming at you with combined gas law. Now, before we get started, I do want to point out that I have posted a review video on Google Classroom. I've also posted it on Edpuzzle. You can find it on the website, and you can find it on this PowerPoint. This is a really great review video that recaps the relationships, direct and inverse, between the four different variables of gases. So that's pressure, volume, temperature, and the number of moles. So, highly recommend that you view this video before we start the rest of this lesson. Of course, it is totally optional, and if you feel really confident with your understanding of those variables, then feel free to continue watching this video. Okay, so we are going to be talking about the combined gas law, which is exactly as it sounds. It's where we take the four previous laws and we smush them all together into one law. That one law is this monster right here in the bottom right-hand corner. The combined gas law combines Charles, Gay-Lussac's, Boyle's, and Avogadro's laws. Now remember, Charles, Gay-Lussac's, and Avogadro's laws are all directly proportional, which means that each of them highlight two variables, two of the four variables, and they are directly proportional to each other. So that means that if one variable increases, the other variable also increases, and vice versa. So Boyle's law is the only law that displayed an inverse proportion, which means that as one variable increases, the other variable decreases, and vice versa. Okay, so we can actually see that all of those relationships are highlighted here in this final equation that combines all four of those gas laws. Before we get into any practice problems or talk about the concepts behind the combined gas law, I do want to talk about your units. We've been doing calculations for 2 weeks now, and so we should feel pretty comfortable with simple one-step or few-step algebra problems with these gas laws, but we haven't really specifically talked about units. Because there are so many more variables in the combined gas law, it's going to be more important than ever to make sure your units line up. Pressure can only be measured in one of these three, or ATM, millimeters of mercury, and then kilopascals or pascals. And you can use any one of those units. That's totally fine. Just make sure that whatever unit you start with for P1 is the same unit that you end with for P2. So for instance, if you are given P1 in ATM and P2 in millimeters of mercury, you're going to need to perform dimensional analysis to convert one of these two values to match the other. We need to have the same units on both sides of the equation in order for the calculation to work. Volume can only be measured in liters or milliliters, and again, it doesn't matter which one it is, but it has to be the same unit on both sides of the equation. Moles, of course, is going to be measured in moles, and temperature will be measured in Kelvin. Now, we've used Celsius in the past, not for necessarily gas laws, but if you are given Celsius in your word problem, which you will be today, you need to make sure that you convert Celsius to Kelvin. And how you do that is with this equation here. So there is no dimensional analysis to convert Celsius to Kelvin. If you take, let's say, negative 30 degrees Celsius, you would plug it into this formula. So it'd be negative 30 plus 273, which would give you 243 Kelvin. So you can see here, these are our four previous laws: Boyle's, Charles, Gay-Lussac's, and Avogadro's. We literally smushed them all together to create the combined gas law. You can see bits and pieces of each of those laws in this equation. P1 times V1, P1 times V1, V1 over T1, V1 over T1, P1 over T1, P1 over T1, V1 over N1, V1 over N1. So again, the combined gas law combines all of those values. So there is a little bit of a demo here. The first demo that I'm going to show you is a ping pong ball. Now, if you guys have ever stepped on a ping pong ball or maybe sat on it and you've dented it, it's not the end of the world. You actually can fix it using gas laws. Think about a ping pong ball. Inside a ping pong ball, there's a fixed number of moles of gas, right? There are no holes in a ping pong ball. It's not leaking. So we have a constant number of moles. Because the ping pong ball is dented, the volume has changed, right? It's a smaller volume. And what we're going to do to this ping pong ball to fix the dent is subject it to heat. So let me show you this video. Here is our dented ping pong ball. Not good. We need to fix it. So we're going to take the ping pong ball and put it in boiling water or hot water. And what that's going to do is heat up the gas inside the ping pong ball. The gas inside the ping pong ball is going to increase in temperature, which means that the average kinetic energy of the particles inside the ping pong ball also increases. Because the average kinetic energy is increasing, those particles are going to be moving faster, and they'll be hitting the sides of the container, the sides of the ping pong ball, with more force. And if they hit it with more force, that means they're increasing the pressure. But this dent, it's not there forever. The force of the gas particles hitting the inside of the ping pong ball pushes the dent back out of the ping pong ball, which increases the volume. So you can see that we've talked about a bunch of relationships just in that one explanation. Let me go ahead and rewind this. Maybe. It won't let me. So you can see as we heat it up, the dent is slowly coming out because those particles are hitting the inside of the ping pong ball to push the dent out and increase the volume. And that is how de-denting your ping pong ball works through the magic of gas laws. I also want to highlight this video here. It's called Egg in a Bottle. Highly recommend that you watch the video. I did post it as an ed puzzle. Highly, highly, highly recommend that you watch it. These guys do a really wonderful job explaining how the combined gas law applies to this video, to this demo. If you start at 1:15, that's the experiment, and then 1:59 for the actual explanation. Now, what I really love about this particular